Hello team, in this video we're going to talk about what's driven the adoption of cloud computing technologies. One main advantage is that cloud computing allows control over resource allocation. So cloud tenants, they can choose how much resources they use and they can control this amount of resources dynamically. For example, a startup usually has few users in the beginning, and as their app or service increases in popularity, more users come along, and then the startup needs more computing resources. So this startup can use cloud computing to just rent additional resources as its user base grows. And similarly, a startup or company can start with a simple deployment on the cloud and then keep adding complexity over time. And as complexity increases, it can rent additional resources to support this complexity. Cloud computing allows not only increasing the amount of computing capacity, but also decreasing. So a company that sells articles, say an e-commerce company, can rent additional resources during Black Friday to absorb the load. And whatever company streams Super Bowl or the World Cup can do similarly, can rent additional resources during the game so that it supports the increased number of users. And then as soon as Black Friday ends or the game ends, the company can release these resources and then pay only for the resources that they actually use. The adoption of cloud computing technologies was the flattening of single thread performance and the move to parallelism, and also changes in how we operate and maintain computing infrastructures. This graph shows a history of CPUs, and it shows time on the x-axis, and it has a logarithmic scale on the y-axis, and it shows different types of data. So in yellow we have the number of transistors on a chip. In blue we have the single thread performance of that CPU. In green, the frequency, the megahertz or gigahertz at which the CPU runs, and the amount of power in watts that the CPU uses. And in black, the number of logical cores. So in this graph, we have two big phases. Up to 2005, we see that most of these measures increased exponentially. So the number of transistors increased exponentially, the single thread performance also increased exponentially, and most chips had a single core. Right? So you had one core on the chip and it became faster over time. And this improvement came from the reduction in size of the transistors, mostly from the reduction of the transistor size. So as transistors become smaller, the amount of time it takes for signals to propagate decreases, and then you can make the frequency faster just because the signal propagates faster. So you can increase frequency, but increasing frequency also requires you to increase the amount of power that you put on the chip. So we see that chips started using more power, frequency increases, and then the single thread performance also increases, and the number of transistors increases because they become smaller. You can pack more transistors in a chip. And this continued up to 2000, more or less 2005. And after 2005, transistors became so small that we couldn't increase the frequency anymore. And this happened because to increase frequency, you have to increase power. And as you increase power, the temperature also increases. And if the chip becomes too hot, then it melts and you can't use it anymore. So we hit what we call the power wall. We can't push any more power into the chip, so the red triangles here became mostly flat, and then we also couldn't increase the frequency, and then single thread performance also started to decrease. The amount, the performance of single threads started to flatten out. It still increases a little bit because of optimizations in the CPU, and you can just make the CPU itself faster, even though the frequency is constant. But the single thread performance is flattening out. But the number of transistors on the chip continues to increase because we can still make transistors smaller. So we have like 4 nanometers now on cell phones, and it becomes smaller every year, a little bit smaller. So what we did was the number of transistors are increasing, and we're using these transistors to pack more cores into each chip. So these days you can buy dual core, quad core, 6-core, octa-core processors, and to extract performance from these processors, we have to build multi-thread applications, because any single thread doesn't run very fast. So if you want to go faster, you have to write these parallel applications to use multiple cores at the same time. So let's have a look at how the move to parallelism impacted how we build supercomputers. So this is a picture of the Cray YMP1, which was the fastest computer in the world between 1988 and 1989. So the Cray YMP, you could buy it with 2, 4, or 8 vector processors. And these vector processors, you couldn't find them on PCs or any other hardware. So these were specific processors built to be very fast and access large amounts of memory, and you only found them on Cray computers, or even probably only the Cray YMP. And so you had to write specific programs to run on these supercomputers. So they were kind of inconvenient to program because you had to build specific purpose code for these computers. And the strategy here was to pack as much computing power on a single chip as you could, and have this chip access as much memory as you could. This is a picture of the NEC Earth Simulator, which was the fastest computer in the world between 2002 and 2004. And here we can see that the strategy changed a little bit. So the NEC Earth Simulator was composed of 640 nodes, and each node, they were called SX6 node. It had 8 vector processors, so this is on each node, and 16 gigabytes of RAM. And to program this computer, so the processors were also specifically built for this supercomputer, so they had their own architecture. You couldn't find this on PCs or other servers. So you had to write specific code, but the architecture was already distributed. So if you wanted to use the computing power of the whole supercomputer, you had to write the program in a parallel way to extract all of its computing power. This is a picture of the Celine supercomputer, which was the 5th fastest supercomputer in 2021. It's built out of these little modules, like this row of servers over here. So this is the NVIDIA DGX SuperPod. And to build a supercomputer, basically they just interconnected many of these superpods. And each superpod uses AMD EPYC processors, which are server processors. So you can buy servers with this processor today. And some of Celine's computing capacity comes from NVIDIA GPUs, specialized for doing calculations instead of rendering graphics. So this supercomputer is built very differently from previous, like the strategies shown on the previous slides. So here we have off-the-shelf components that you can use on your company if you buy a server. And so this makes these supercomputers easier to program and maintain. So I used the previous examples to make things a little bit concrete, but this graph shows an overview of this evolution of supercomputing. So here we have on the y-axis the number of systems in the top 500 fastest supercomputers in the world. Over on the x-axis we have the time, and each color shows a different computer architecture. And what we see is that in the past there were many architectures competing for being the fastest or most efficient. So the top 500 supercomputers, were a mix of different architectures that kept computing with one another over time. And then some architectures went away and some new architectures came along. But after 2006, we see a consolidation, and most of the supercomputers these days, they run on Intel's architecture, which is exactly the same we have on our computers. And one of the reasons for this is that using cheaper components makes it easier to maintain and operate.